Hello and welcome to 8th and the last lecture of 7th chapter in our comprehensive course on AI, machine learning and DS. The name of this chapter was Data Wrangling with Pandas. Previous chapter was also about pandas, but there we used only one thing, how pandas is used to do exploratory data analysis. In exploratory data analysis, we just explore the data. For example, if it is numeric column, then what is the mean, what is the minimum value, maximum value, what is the median, what is 25th percentile, 50th percentile, 75th percentile, and like that. We also detect if there are outliers, if there are duplicate rows, but just detect, we don't do anything. We don't modify the given data. While this chapter is data wrangling, so here we even treat if there are outliers, we learned how to remove them. If there are duplicate rows, then how to remove them. If there are single valued column, how to remove them. So this is now data pre-processing. Data wrangling in more scientific language is called data pre-processing. Now, last topic in the data pre-processing was about normalizing and standardizing data. And as it is an important topic and requires in-depth discussion, previous whole lecture was about normalizing, and now this whole lecture is about standardizing. What is normalizing or what is standardizing? Now, sometimes the data is like this. So the problem with this data is that the scales are pretty different. For example, what is the minimum value of income? Then maybe 45,000 and the maximum value is 65,000. But it is of the order of 1,000. Age, its minimum value is 25 only and the maximum is 45. And education, minimum 12 years of education and maximum 18 years of education, like that. Now, the issue is that if I use this data as it is, then what will happen is this, which has very large scale and large big values, that column will dominate the prediction, or that column will have some undue influence on the prediction, and therefore we will get that way a kind of inaccurate model. So what we try to do is we try that all variables are of the same scale or of the same order. We don't want such big differences in order of variable. So one way is normalizing, which we had already done in previous lecture. Here everything is scaled from 0 to 1. So for example, income will also be scaled from 0 to 1, age will also be scaled from 0 to 1, and education will also be scaled from 0 to 1. Somewhere earlier, we had also obtained that data frame, and that is after doing that transformation. And you can see here, income varies from 0 to 1, age 0 to 1, and education 0 to 1. So now no feature will unduly affect the outcome variable. Okay, so that process of converting all variables into 0 to 1, this is the same data, and you can see here the ranges are very big. Now this is also the same data, but the ranges are identical 0 to 1, and we also saw that though the range is completely changed, this is the original data on the left side and this is the data after we do normalization, but though the range is completely changed, but the data distribution is identical. There is not even a fraction of difference between the data distribution. That is the great thing about normalization. Okay, and we did this normalization with min-max scalar. Okay, min-max scalar. Now we want to do standardization. So this particular this one, actually it is yes, this I have copied from earlier same markdown cell, just for the sake that you can remember. Otherwise, before starting normalization also this paragraph was there, and now before starting standardization also. Both normalization and standardization are called scaling, but I personally don't like to use word scaling because it might create confusion and it is not appropriately indicator of what method was used to scale. Okay, now normalization scales the data from 0 to 1. Standardization scales the data in such a manner that all the columns will have their mean at 0 and all the column will have standard deviation equals to 1. Therefore, variance, which is nothing but the square of standard deviation, that will also be equal to 1. Now, why we need this? That is because there are certain algorithms which first require data in standardized or normalized form, and at the same time now there are some modern algorithms to which I can even feed this type of data, that is unstandardized, this type of data, and they will work. But they also internally first do normalization. That means they convert this data into this type of data internally, and then they do the modeling process. So ultimately they also do this standardization or normalization. Okay, now so there are two types of algorithm. For one, you have to manually do normalization and standardization and then feed the data to the algorithm, and for others you just feed without, it doesn't care. But the built-in normalization methods are often some data scientists think that they are often wanting in the customizability. So if a data scientist wants to control the normalization process, then he can select normalize equals to false in those algorithms who can themselves normalize. But even in them, there is an option. You write normalize equals to false, then in that case, they will not do normalization, and you still have the option that you can do manual normalization or standardization. We did this, how to scale the data from any given range to 0 to 1, and we saw that data changes, but data distribution does not change. Okay, now we are doing this standardizing, that is how to change every column of a data set into such values so that they have 0, mean, and 1 unit variance. That format is called standard format. Okay, now it is important to do this because there are certain algorithms like gradient descent or k nearest neighbor. Okay, now gradient descent is practically it is embedded in almost every algorithm as a concept. Okay, and k nearest neighbor also. Both these we are going to learn in much depth, but they work better if the data which you feed to them is normalized or standardized. Okay, and converge faster. Now converge faster means what? These algorithms do several iterations. So they pass through the entire data once and try to find the best solution. Then they pass through the entire data second time, third time, fourth time, sometimes 100 times, sometimes 500 times, like that. Now, if you don't give them normalized data, then also they will converge ultimately and find the model which is the best model. But one, that best model is only best among those unnormalized data, the models given by unnormalized data. And second, it will take a lot of time to reach that best model. On the other hand, if you supply it with either normalized data or standardized data, then in that case, they will quickly converge. So for unnormalized data, if they take 500 iterations, then it is possible that for normalized data, the algorithm will converge and it will give the best model in only 100 iterations. So let us do the normalization process. First step is just creating my data frame. So I am creating the data frame. Here, this line should not be here, okay, but ideally, let me put, because here it has no use. And here it should be, okay. Now, here only pandas is imported and we create a dictionary. We all know repeatedly I have said, so now you should be able to tell me that these all will become column headers and this list will become rows. So how many rows will be there? 1, 2, 3, 4 and 5 rows. These are the values under income column. These are the 5 values under age column, and these are the 5 values under the education column. And this is the data. This is the same data as we took earlier. Let us do describe so that you can know that at present what are the mean and etc. Then at present, forget about the first line that just shows the number of rows and that are equal, but mean of income is 54,800, mean of age 32.6, and mean of education 15. That is the problem, that such data is not very conducive for many of the machine learning algorithms. Their ranges, mean, their various statistical parameters, they are far different. Say these are minimum 45,000, these are only 25, and these are only 12. So these two are more or less on the same ground, age and education, but this is too high, and therefore it might unduly dominate the model, and the model which you create by using this kind of data will have bias. So what we do, this was earlier min-max scaling or normalization that I am keeping here so that you can compare the steps, that the steps for standardization are identical. So this was what we did in earlier previous chapter. Okay, so now so that's why I have put in markdown column. So it is not a code but markdown. Now apply standard scaling. So standard scaling means this converted the rows into what minimum value of all columns was 0 and maximum value of all column was 1. While this will convert all columns in which way? So that the mean value of all column is 0. Now here you can see currently means are far away from each other, not good. But if after applying this process, the means of all will be 0 and the standard deviation of all will be 1. Okay, so let us do that. Steps are exactly identical from sklearn.preprocessing import. If you want to do min-max scaling, that is normalization, then import min-max scaler. But this time I want to do standard scaling, or that means standardization. So then I will import standard scaler. Then next line is also same. Here we created an object, scalar object, using the imported min-max scaler. Similarly here I will create a scalar object using standard scaler. Okay, and then I apply that scalar object to my entire data frame. So scalar.fit transform df to entire data frame, and still you have to specify to which column you want to apply. So I am saying df.columns. Df.columns means all columns, all 3. Okay, and similarly here I am applying scalar.fit underscore transform data frame and columns is equal to df.column. So after you do first 2 steps, The next steps are exactly identical because the only difference between the two is technique. Here the technique is min-max scaling. So we apply min-max scalar, import min-max scalar and create that scalar. Here the technique is standard scaling. So we import that and create that scalar. Once scalar is created, thereafter it is always scalar dot fit transform. This initial step you should not forget because one limitation of this scalar object when it is applied to entire data frame or subset of columns is that it does not return as a result a pandas data frame object. So you have to save it or convert that into pd dot data frame. Okay, so pd dot data frame when you write, and then let us print my scale data. Now this was my original data frame. Sorry, now this describe I am this output I am just deleting. Okay, so that this was my original data frame and this is my scaled data frame. So I can see this time that what has changed, what is the mean value of this that I can find, and what are the standard deviation. So again I will do describe, and if I do describe, then the mean of this is 2.22 into e to the power minus 17. That means exponential minus 17 or 10 raised to minus 17. But that is so small a number, 0.0000016 zeros and then 222. But that is nearly zero. It is actually exactly zero, but our computer has a limit of floating point calculation, so it does not become exactly zero. But you can understand after 0, 16 zeros are there, and then 222. This is even smaller, slightly larger, but again it is e to the power minus 16. So that means 0.00015 times 0 and then 177. Okay, and this is exactly 0. So how my data has been transformed, the mean has become 0. And what is the standard deviation if you see, then it is nearly 1. 1.118, 1.118, 1.118. Okay, so the standard deviation is 1. So this type of transformation is called standard scaling, or it is also called standardization, where each and every column will have mean 0 and standard deviation equal to 1. Okay, let us see if by doing this I have not disturbed the data distribution. So plotting again, you don't need to bother how this code was written and all that. At present, the purpose is just to clear the concept because matplotlib and all its discussion will come later on. So this is the distribution for the original and this is the scale. You can see that scales are completely different. Here 45,000 to 65,000, while here it is minus 1.4 something to plus 1.45 like that. But that is okay. But data distribution, if you see, there is not even a fraction of change in the data distribution. Here also scales have changed. 25 to 45 has now become again minus 1 to 1.5 like that. But data distribution is same. You can even plot the kernel density plot so that you can see that normal distribution, etc. So this before doing standard scaling, this was income column. After doing standard scaling again, this is age. This is the age. You can see there also there is absolutely no difference. So any result which are obtained by taking this original data and the results which are obtained by taking this, that is the new scaled data, they will be exactly identical. In fact, this result will come much earlier and they will be perhaps higher in quality. Okay, so standard scalar is that technique which first standard scalar we initialize and we applied that standard scalar to data frame, that is df.fit transform. We do scalar.fit transform standard scalar and in the bracket df, and we also clarify that columns equals to df dot columns. That means we apply the scaling to each and every column of my data. Now with this chapter is over and this is the exercise. As I said in the previous chapter also, don't be confused by 7.1 and don't go on searching for very 7.2 etc. because earlier it was thought that I will take a whole panda in one big chapter. So 7.1, 7.2, but then I made 3 chapters out of one chapter. So these are only 7.1, so that is fine. This is a part of question. So again, you don't have to be confused about how this all code is written, and this is just a data frame which I have to give you before I tell you that please wrangle this data frame. That is, please do data pre-processing on this data frame using pandas. And data pre-processing means what? The first question does first thing handling missing values. Then second does data type conversion. Third does outlier detection and removal. Fourth does duplicate row detection and deduplication. Fifth does single valued column dropping, and sixth does normalizing and standardizing. So it will be a very good revision of entire chapter. Okay, this data frame would be automatically created, so you don't have to bother about that. Okay, now with this we end this chapter. Thank you and see you in the next chapter.